Welcome to solverfy.
Polyprotic acids have multiple hydrogen atoms that they can lose, so they can act as buffers in multiple pH ranges. Carbonic acid, or H2CO3, loses its first hydrogen to become HCO3-, which is carbonic acid's conjugate base. But since HCO3- still has a hydrogen to lose, it can act as an acid, where in the second reaction it loses its last hydrogen to form CO3 2-, HCO3-'s conjugate base. Carbonic acid has two Ka values because it has two hydrogen atoms. So Ka1 is representing this first equation, the loss of the first hydrogen here, and Ka2 is representing the loss of the second hydrogen. Let's look at a buffer that contains KHCO3 and K2CO3. Both of these will completely dissociate in water into potassium ions and their respective ionically bonded polyatomic ions. HCO3- is in both the first and the second equation, but CO3 2- is only in the second. So we know that we're dealing with the second equation here, and therefore Ka2. So now that we know which Ka value to use, we can solve for the pH of the buffer using the Henderson-Hasselbalch equation. The pKa is the negative log of the Ka. So the negative log of 4.7 times 10 to the negative 11, since we're using Ka2. And this is equal to 10.3279. So now the pH is equal to 10.3279 plus the log of the concentration of the weak base, which in this case is CO3 2-, over the concentration of our weak acid, which in this case is HCO3-. So if we have 0.22 molar KHCO3, there's a 1-to-1 ratio between KHCO3 and HCO3-, so there will be an equal concentration of HCO3-. Then if we have a 0.37 molar concentration of K2CO3, there's a 1-to-1 ratio of K2CO3 to CO3 2-. So again, we will have an equal concentration of that as well. So we can plug these values into the equation. So the log of 0.37 over 0.22. This is 10.3279 plus 0.2258 or 10.55 with the correct significant figures.